All right. Hey, we're going to jump into just kind of a realistic workflow of how I approach developing quantum circuits. It can seem a little overwhelming sometimes when you have this problem and you're limited on the amount of quantum computation that you have, and you don't even know if it's going to work or not, and how I go about tackling that. So, first of all, you're going to have to select, what kind of problem you're trying to solve. You're then going to map that to your quantum circuit with both the feature encoding and your ansats. And then from there, I go to toy testing, which is basically a small version of the problem that I'm trying to solve. So if I'm hoping to scale to 50 qubits, I start between 5 and 10, much, much smaller, and I create that toy. I'm going to then test that toy and include noise and things, and then it'll be time to scale it up. So I'm going to kind of walk through that process. Selecting and defining a problem. So you're going to identify your target problem. It could be optimization, some type of, quantum simulation or classification. You need to have a reason why quantum approach might help. Dr. Mukesh was saying that, like, hey, we're never playing video games on quantum computers. It doesn't make sense. So what we're looking for here is, hey, this is a huge combinatorial landscape that I want to, try to represent a large, all the possibilities at once to some extent, or that there's some type of non-linearity in how these things are located or how these things are related. So we're hoping that a reason a quantum approach might help. And then you're going to want to define your goals, accuracy, runtime, cost, scalability. Sometimes with quantum computing, we're not really improving accuracy, we're reducing how long it takes to get these results. Or sometimes we are increasing accuracy without that improvement. Ideally both, but, we need to take a look at what we're hoping to get out of applying quantum. And then we need to have some type of classical baseline for comparison if this is classically tractable. We want to know what we're working with here and what we're working against. A big aspect of how to identify a problem, what it is you want to work on. The biggest thing I see here is, like, read the literature. Once a week or so, hop on, Google Scholar, type in quantum computing plus, whatever field of interest you're in, and see what other people are doing. And the big thing I would say is to look for similar type problems. Okay, hey, someone has this algorithm, they're solving this kind of problem with it. If you can look at this and go, hey, that problem kind of looks like this other one. The energy function they're using here kind of looks like, estimating the shortest path in this graph theory type problem, or some other thing, where you look at this and you're like, oh, I wonder if that would work for this other thing that's similar. Now, of course, you're going to have to do some modifications, of course, to theirs, but, like, I think it's better to try to look to build off of what other people are doing than trying to completely build up from the ground from scratch. Another aspect is, if you read survey papers, oftentimes, if you're writing a survey, rarely do you just want to purely reiterate what everyone else has said. The idea is that there's supposed to be some kind of synthesis here when you're writing a survey. And so what you're able to do oftentimes when you're reading these surveys is they'll point to problems. Hey, a acceptable benchmark between these algorithms doesn't exist yet. It would be interesting to apply this sample-based quantum diagonalization to this other domain. So oftentimes people who write surveys, they spent months and months reading this material, and they can spot these holes or gaps that are, what their contribution is to just a big literature review. Another aspect is that Qiskit is open source. If you go to github.com /Qiskit, you can click on libraries and see what their open problems are. Now, this is a little bit less research, pure research, but oftentimes if you're wanting to get involved, these problems are open source. You can click on the issues tab at the top of the GitHub site, and you can try to find a good problem. And oftentimes they'll have certain problems flagged with good first issue or something like that. So there's another way of identifying something where you can make a contribution. The next step is deciding how we're going to map this to our quantum circuit. I've talked a little bit about, like, just in passing with Z feature map, ZZ feature map, efficient SU2. There's various methods of encoding your data into your quantum circuit. And so, the three main types are basis encodings, where you have a quantum register. Say I have 3 qubits, I can represent any value between 0 and 8, or yeah, not including 8, 0 and 7. You can encode it in the amplitude, the how far 0 or 1 it is, or like phase rotations. There's trade-offs with all of these. Basis encoding is the most expensive in the terms of qubits. Amplitude encoding is most efficient, but is the most costly in pre-computation. You have to build these states, and it's very expensive. And then generally phase encoding is a acceptable trade-off. Another aspect of this is that we're going to talk about our toy model in a second, but you don't necessarily have to commit to one right from the beginning. You can make a toy model that you're testing out various different encoding styles to try to get an idea of what works and what doesn't. All right, then you're going to have your ansats. This is the problem-solving part of your quantum circuit. And there's a lot here as well. I highly recommend lean on the literature, lean on publicly available GitHubs. There are very open types of ansatses that are just hoping to generally learn a set of parameters to get an output. And then there's some very problem-inspired ones where, hey, I'm modeling this molecule, or I'm optimizing for this financial problem, where I make a bespoke quantum circuit to try to, look, I'm going to entangle these features but not these because I know these are important to each other, things like that. And then with your ansats, you'll also have to consider how you're optimizing this. There's gradient-free optimizers that are, more robust to noise, and there's gradient methods, and that affects how many shots you take and how suitable your circuit is. Now, here's the big thing I want to push. My first step, once I've selected a problem and I have an idea of how I want to build my circuit, is I build a small toy model. Okay, I may plan on using 50 qubits, but as a toy model, I'm going to do 5 to 10 qubits, something like that. And a lot of this is, one, to just get code that runs. Hey, can I take the type of data I'm looking at? Can I run it through this quantum circuit, and can I get a meaningful output at the other end? There's an aspect of getting it to run, but then I can also scale this. It's not just toy model full production. I make 5 to 10 qubits, and then I can add some noise to these qubits. I can see where is this noise coming from. Then I can start identifying how am I going to mitigate this noise. And so I can, and there's a lot of methods to this. Hey, should I redesign my circuit where the entanglement makes sense? Hey, should I map this directly to qubits? Should I just run zero noise extrapolation or dynamical decoupling? But this is really hard to do whenever you've already scaled up to your full 50, 100 qubit system. Each run takes minutes of your quantum computation time. It's a lot of times it's more difficult because you can't simulate at this level. So I think it's really valuable to, at the level where you're simulating, to evaluate what type of noise your system is subject to. Okay, so we simulate our toy model. We see how noise is going to affect the circuit. Remember, you can simulate noise. You can specify a noise model from a backend of the real hardware, and you can simulate with that level of noise to understand how that affects its circuit. Once you understand how the noise is affecting your circuit, It's time to test how your circuit performs on the real hardware with those noise mitigation techniques, whether that's, hey, direct circuit mapping to, make sure that I'm measuring on qubits that have low measurement error, or whatever the case is, or zero noise extrapolation, dynamical decoupling. And what you're wanting to do here is to see, okay, am I able to get meaningful answers out the other side? And then it's going to be time to scale up. And it depends on how much scaling up you need to do on how many iterations of toy models you need. If I'm trying to design a 100 qubit circuit, my first step might be to have my workflow work on 5 or 10. All right, see how noise is affecting this circuit. And I can even, compute and uncompute with the unitary overlap like I showed in a couple sessions back. That way it matches the length that it will be when it's scaled up. But I can understand how noise is affecting this to where I'm not using up a bunch of quantum computation time. And additionally, though, is that my problem's not so complex. At 10 qubits, I can kind of understand of like, okay, the noise is coming from here. Whenever my circuit's not very wide and not very deep, I can better understand what's going on with it. But, if I'm scaling up to really large problems, and especially if I'm expecting to repeat these computations a lot of times, I might do, a check at 5 to 10, a check at 20, a check at 30, and with that, some of that circuit folding where I'm computing, uncomputing, and recomputing, that way I can see the effect of the depth on my circuit. And before I go to that full 100 qubit deployment, which your simulator's not going to be able to handle that size, but I'm going to want to scale up my simulations and my noise to where I better understand what's going on there. And so it's kind of an iterative process whenever you're designing a new quantum circuit. And here's the biggest thing is iterate and document. I don't care what your method is there, but you need to capture what you're doing. Now, here's the thing. My iterate and document is oftentimes copying a notebook and changing variables and running it again and saving the old one. Hey, it's there if I need it. I can save all my notebooks into a folder. I can label it, Luke's awesome quantum circuit, 10 qubit, 20 qubit, 30 qubit, to where I can scale up and see what I've done and compare my different approaches. But it's one of those things where I know I've gotten into bad habits coming from a machine learning background where the compute's relatively cheap, and I put together this monster network with all this pre-processing and all these other things, and I click run and it runs for an epoch or something and crashes out. Oh well, no big deal. But at the same time, we have 10 free minutes a month. And oftentimes, too, with a large circuit, you might have to wait 10 minutes or an hour during busy periods for you to get in on the quantum hardware. So it's a little more important to better understand what's happening here. And, we deal with noise from the data side with machine learning, but understanding how the noise is going to affect your circuit on the computation side, which isn't something we're used to thinking about, is also, just really, really important to take time and to model your circuit, to evaluate how noise is affecting it, to evaluate how your different noise mitigation techniques are affecting it. Yesterday I showed off those notebooks where I ran my circuit and I tested it with, this error mitigation technique, and then these 2, these 3, these 4, each one of them separately. And it's doing those things are what's going to allow you to, 1, save your quantum computation time and not use it all up, but also 2, be able to get the best answers out the other end that are possible. Any questions, anybody? All right. Well, anyone's thinking about questions, a little bit of housekeeping as we wrap up Kiskit Fall Fest. Tomorrow we are having the hackathon on the 4th floor of the Miller Nichols Library. We have 8 posters that have made it through that are going to be competing on the quantum track for the $1,800 in prizes. For all the people who have attended the sessions, please make sure that you get in your video attestations. That way you are eligible for the raffle for the Kiskit swag boxes. And I will be sending out certificates of participation early next week. This afternoon, I'm going to be adding links to all the slideshows that I've used throughout the Kiskit Fall Fest here, and I greatly appreciate all of you taking the time. Yep. You're welcome. Yeah, so that's where that's at. Let's see. Final notes. So we have the hackathon tomorrow. We have our Qusaic meeting on December 11th at 1 o'clock on the first floor of the Plaster Center. Join Qusaic if you haven't yet. I'll send out a link for that. And I look forward to continuing to interact with all of you. Have a great day.